Alright, so enough with the little kid examples. I saved a nice one to complete this sequence of examples, this lecture. Save the nice one for last, and that would be this one right here. Super famous substitution. U equals tangent of x over 2. No one would think that that would solve that one. Some mathematicians have called this the sneakiest substitution in the world. Alright, let's take a look. It's fun. It turns out that this will be our dictionary. So this is our dictionary. I'm gonna make some space here for our dictionary. This dictionary is actually kind of special. So in fact, I'm gonna make it a little bigger. No, actually, you know what? I'm gonna take the whole page for the dictionary, and then we'll do the problem on the next one. So the dictionary starts off like this: U is equal to tangent of x over 2. Remember how we said that the dictionary is sometimes you invent, you create, it comes out of divine inspiration, and sometimes you just copy it from others. This one's copied from others. One guy had the brilliance come up with this, and watch what happens. You copy this definition, substitution, and I need a differential. So du, the derivative of u would be secant square x over 2 times 1 over 2 times dx. Okay, and eventually I'm going to have to solve for dx here, so maybe I'd like to isolate it here and solve for it. I would move the 2 over there. That would give me 2. I would move the secants over there. They look like cosines on the other side, because that's what a secant is when you flip it. Du is equal to dx. That's the exchange rate for a dx. A dx can be exchanged for that. It's good, not completely clean. Maybe this has x's in there. Maybe we can substitute out of that x's. For that, we need to look at our original dictionary and maybe draw a right triangle to help us with the translations. The right triangle would look something like this, where the angle here is x over 2. This is telling me that the opposite ratio is u to 1. Opposite to adjacent is u to 1. That forces the hypotenuse on this one to be u squared plus 1, and that immediately tells me what a cosine would be. Cosine would be this ratio right here. That ratio, the adjacent to hypotenuse, would be the cosine ratio. So and then I have to square it. This is 1 over that square, so this would give me 2 times 1 over the square root of u squared plus 1, and I've got a square there, times du. That's how much a dx can be exchanged for. And you could clean it up a little bit. U squared plus 1 du is equal to dx. That part will go right here. So I know that much of the dictionary. That'll go there. I've got sin x there, and I don't have sin x anywhere in my dictionary. But I do have a triangle that tells me the ratios for x over 2, but I need one for x. Whenever you've got sine of x over 2, but you want sine of x, you might want to think about some double angle identity that translates, that tells you the exchange rate between a normal angle and half the angle, or going that with a double angle. The one I'm thinking about, because this one I can look at the triangle here. The ratio would be opposite to hypotenuse. The identity that I'm thinking about would be something like this. Sine of 2 theta is equal to 2 sine theta cosine theta. That's famous, and if we apply it to our case here, this would tell us that sine of x would be equal to 2 times sine of half of x and cosine of half of x. These ones I can easily get because I can look at my triangle from the dictionary. So I would get that sine of x is equal to 2 times sine of x over 2. That would be u over the square root of u squared plus 1. And the cosine would be the ratio 1 over the square root of u squared plus 1. When you put that all together, you get that sine u can be exchanged for that. Duh. Nice, huh? That piece, that's what's going to go here in my substitution. Okay. Next, I need to figure out what would I substitute for cosine x. Many ways to go about it. Maybe we could try to figure out an identity that has double x and single x, or double angle or half angle with cosine. And I think there's a famous one. For example, this is a famous one. It goes something like this: cosine square x is equal to 1 plus cosine 2x all over 2. You guys seen that one? And everybody's seen that one. Or you could put thetas or whatever. You can rewrite it here. It also means that cosine 2 theta is equal to 2 cosine square theta minus 1. This is another famous one. It's a different version of that one. Either one of these would work. Let's go with this one. Applied to our particular problem, I want to know, how can I write cosine of x using half of it? It would have to be 2 times cosine of x over 2 square minus 1. This would be a different version of the same identity. This is a particularly nice one because I have a cosine x over 2, or I have an x over 2 ratio. So I would just have to pick up the ratios here adjacent to hypotenuse, plug it in here. Talk is cheap, let's do it. Cosine of x would be equal to 2 times cosine ratio, that's 1 over that, square root of u square plus 1. But I'm squaring it, so I'm squaring it, minus 1. So the cosine x, you guys can barely see there. Give you some more room here. Cosine of x is this gives you, when you square it, 2 over u squared plus 1. I have to subtract 1, but I might as well get a common denominator on that. U squared plus 1, u squared plus 1. That way I can combine these two. That would give me cosine of x is equal to 2 minus 1 minus that, so it'll give me 1 minus u squared all over u squared plus 1. And that would be the exchange rate for cosine. Okay? How are we doing so far? All this is, of course, just working on the dictionary. I told you this is a fun one. But this is super famous. It's called the Weierstrass substitution. In practice, most books don't derive this, every single time they do the problem. They do it the first time, and then after that, they just remember, hey, I remember this was the result, so they put it in a box, and then they come back and use it every time they want to. You could box that. You could box the differential here and say, hey, I'm just going to remember that. But you don't want to just remember it if you don't know how to do it yourself. You should only do that after you've really owned it, make it your own. Just like we're doing here, trying to derive it, understand where it comes from. Alright, all this was just so that we could make the dictionary, and now we will actually apply it here and see how it goes. Alright, so I cut and pasted on a clean page so that we could just remember what our work from the dictionary. So I go here, and this becomes the integral. I'm going to do the translation here. It becomes 1 over 5 times cosine of x. For cosine of x, I'm looking here. That would be 1 minus u squared all over u squared plus 1. And then I have plus 3 times sine x. For sine x, I'm looking there. So that would be 2u over x squared, no, u squared plus 1. All that times du, or dx. For dx, I'm looking here. So that would be a 2 over u squared plus 1 times a du. This will get distributed, just to do my algebra correctly. This gets distributed there. I'll put some color in here. That gets distributed in there as part of the simplification. That becomes 2 over 5 times 1 minus u squared plus 3 times 2u. Whoa. 2u, because what happens is this cancels the denominator there. It also cancels the denominator there. You're left with a du here, and amazingly, all we have now is just a polynomial on the denominator. A polynomial that looks roughly like this. It looks like 5 minus 5u squared plus 6u du, or maybe it looks like this: 2 over, let's just go with 5 plus 6u minus 5u squared du. Okay, that's beautiful. That's a polynomial. We have many techniques to solve that one. Well, for example, you could complete the square and do a trig substitution. Turn a binomial into a monomial. You could try to factor and do partial fraction decomposition. Or you could do both, maybe complete the square and do partial fraction decomposition. Your choice. I wonder if I should finish it. Do you guys want to see the end of it? Alright, so here we go. First of all, I'm going to try to clean it up and pull out some of these constants that are not doing much for us. I'll pull out a 2 and a negative 5 from the bottom. That would give me a 1 over a u squared minus 6 over 5u minus 1. It's not a necessary step. It'll just clean up the algebra a little bit. Because what I'm trying to do is complete the square on the bottom. If I took out a negative, this would make it positive. That would be negative. Of course, the last one would be positive. Now, I go on to complete the square. My complete the square step would go something like this. U squared minus 6 over 5u. I want half of that 6 over 5. Half of it, and then square it. So that would be 3/5 squared. That would give you negative 9 over 20. That would be 9 over 25. And then I have a plus 1. And then just to be fair, I should subtract the one I added. So I should subtract the 9 over 25 that was added on there. That would keep it nice and fair. Okay. When you pull out this negative, this became a negative. This becomes positive. This becomes negative. That becomes negative. I'm gonna check my signs here. I think that should be negative 1. All right. So then you clean this up. It becomes 2 over negative 5 integrals 1 over u minus 3 over 5. Quantity squared. That's this piece. Minus 1 minus that becomes negative 25 over 25 and 9. That would give you 34 over 25 du. That would become 2 over negative 5. Oh my goodness. Now we can make another u substitution and just clean this up a little bit. I'll make the w substitution here. W is equal to u minus 3 over 5. The differentials are straight up exchange. dw is equal to du, so this becomes the integral of 1 over w squared minus 34 over 25 dw. Hey, wouldn't it be nice if we could get rid of this 34 over 25? It's kind of an annoying one. Want to get rid of it? I would like, make me another substitution. Here, I'll show you a little baby trick. I would like w squared to be equal to 34 over 25 times a v squared. Why? Because if I had a coefficient of 34 over 25 here, I could get rid of that. So really, I would like w to be equal to the square root of 34 over 25v. So then my dw would be worth square root of 34 over 25 dv. But w squared would fit right into there, and that would give me 2 over negative 5 integral of 1 over w squared, which would be 34 over 25 v squared minus 34 over 25 dv times square root of 34 over 25. And of course, that's my dw. I substituted dw. And this is nice because this can come outside and you can clean it up really nicely. So that gives you something like 2 over negative 5. I'm taking this guy outside. I could flip it because it's on the denominator. So it'll be 25 on the top, 34 on the bottom. I can also take this outside. It would be the square root of 34 over the square root of 25. And inside I'm left with the integral of 1 over v squared minus 1 dv, which is something nice. Ooh, something very doable. And this thing is noisy. Alright, can you see? Oh, you can see. Alright, so then we could solve this one. And this one we could either solve by a famous trig substitution, or you could solve by partial fraction decomposition. I'm going to stick to trig substitution. Yeah, and I'll go on to the next page and solve this one. Maybe we can deal with the constant later. We could just focus on this for now. Alright, I told you this was fun. So we have the integral of 1 over v squared minus 1 dv. I'm going to go with the substitution v is equal to secant square theta. The reason for that is because secant, The reason for that is because secant square theta minus 1 will turn into a tangent, which would be a monomial, which would be really easy to integrate. This is a common technique from the past, so I won't spend a lot of time on it. At this point, we're doing big boy substitutions, or big girl substitutions, grown up girls. I'll just be quiet. Alright, this becomes integral of 1 over secant square theta minus 1. dv becomes secant theta tangent theta d theta. This becomes a tangent, so that becomes 1 over tangent square theta duh times the secant theta tangent theta d theta. You can cancel one of these, one of those. Now you've got a secant, which is a 1 over cosine theta. That's your secant. And then you have one tangent left here, which is a sine theta over cosine theta d theta. And I reckon that becomes, just the cosines cancel, that becomes a cosecant theta d theta, which of course is famous. It's the ln of absolute value of cosecant theta minus cotangent theta plus a constant. Wow, that was nice, huh? And now you have to go back and you have to exchange, change all your things here. Use your dictionaries. So secant theta is equal to v. That means that cosine of theta is equal to 1 over v. That means my triangle looks like adjacent is 1, hypotenuse v. This would be the square root of v squared minus 1. So cosecant would be this is a ratio of the opposite of sine. So it would be this ratio. It would be v over the square root of v squared minus 1 minus cotangent. That's this ratio. Adjacent over hypotenuse, or opposite, so that would be the square root of v squared minus 1, and then that would be plus a constant. And now I go back to my previous page and substitute my v's. Where are my v's? So now we're going to have a little substitution party here, back substitution, everything. Just to make it easy for us, I wrote them here. Well, there you go. I wrote them here just to make it easy for us, all the substitutions that we had. Well, let's see, you can't see it. Here is our integral, and those has v's, and here's the dictionary that has v's and w's, and then here's the dictionary that had u's and w's, and then here's a dictionary that had u's and x's, which is ultimately what the question was posed as in terms of x's. So I just keep on going with my substitution, with my back substitution. So it will be ln of v. Instead of v, I have the square root of 25 over 34. Square root of 25 over 34 times w. That's what v is equal to. I flipped over to 25 over there. And then I have the square root of v square. V square would be 25 over 34 w square minus 1 over the square root of 25 minus 34 w square minus 1. That's what it looks like with w's. And now I'm here. I've got the v's out of the way. I've got w's. I want to go for u's now. So wherever I see w, I'll substitute u is equal to that. So it'll be, yeah, this was not that exciting. It's almost boring from here on. So w would be u minus 3 over 5. And on the bottom I have the square root of 25 over 34. I know some of you guys may be thinking, why doesn't he just simplify? The square root of 25 is 5. Yeah, that's a long story. But simplifying is for the birds. Kills your soul. Pattern hiders. If you every time you simplify, you hide patterns. It's really a bad thing to do. That's what happens when your math teacher is your PE teacher in high school. Alright, square root of 25 over 34 w squared. That would give me u minus 3 over 5 square minus 1. Nice. Plus a constant. So now I'm up to the w's. So I'm up to here. And finally, wherever I see u, wherever I see u, I should substitute tangent of a half angle of x. And finally, I will have the answer with x's. I'm going to leave that piece up for you to do. Just rewrite that. Wherever you see w's, you write that. We're going to call it a day. That's u subs for grown-ups. Alright, we'll see you guys next time.